So this is a practice exam from 2020, and a lot of the multiple choice questions are the same as we've seen in the previous video. So the first practice exam, if you've already seen them, you should know the answers, right? And if you don't, maybe pay attention to that question. But then the long form questions, those are all going to be new. So the first one says, the surface integral of b dot dA is equal to 0. Why? Hopefully you remember that in magnetism, we don't have any magnetic monopoles. We only have dipoles. So there's always a north and a south side to our magnet. And then our field lines come out the north and then back in through the south. So then whenever we draw a closed surface, so like a sphere or a cube around our magnet, anytime we have a magnetic field line going out, well, it comes back in at some later point. So here it goes out and then it comes back in. So then whenever we're talking about a net flux, like how many field lines are going out minus how many are going in, we're always going to have 0. So the answer is A. We always have magnetic dipoles. All lines leaving the north enter back through the south. 2 says if we fully charge two capacitors, C1 and C2, so I'll just draw that out. We have two capacitors, and fully charging them means we let the maximum amount of charge sit on them like this, and then we disconnect them from the battery. So we remove this here, and then we connect them with opposite polarities. What happens to the energy? Opposite polarity just means here, instead of having plus and plus on the top, we have plus and minus. So it's minus and plus. So these two have opposite polarities, and that's what it's trying to say. So what happens to the energy? Well, here we notice that we have an attractive force. So see these positive charges, they're gonna move down here, and then the net positive and negative are gonna cancel out. So we're essentially going to lose some of our positive and some of our negative. This decrease in Q leads to a decrease in the energy, because the energy is equal to 1/2 Q squared over Z. So because we have less charge building up on our capacitor plates, we have less energy stored in the system. So then the answer is B, it's going to decrease. 3 says a magnet is dropped through a loop north end first. As it approaches, then leaves, what is I induced? So here we have north and we have south. We're going to look at the north side's magnetic field lines. As it's dropping, the magnetic field lines going down increases. So according to Lenz's law, we're going to have an induced magnetic field going in this direction, which means the current induced has to be going counterclockwise. This is by the second right-hand rule, where you stick your thumb in the direction of B and your hands wrap around in the direction of I. So then in the next scenario, when our magnet is down here, we're getting less magnetic field lines going down. So then by Lenz's law, we get a magnetic field pointing down, and to get that, the current has to be going clockwise. So the answer is B, counterclockwise, and then clockwise. 4 says, what is the effect of an ideal zero resistance inductor on the current in an RL circuit with a DC current after a long time? Hopefully you remember this graph here, where we have time and we have current. And we know when there's an inductor, it takes some time before the current reaches its maximum value, but then it plateaus at that value, I max. So after a long time, we're in this region here, where the current is just its maximum current, so the inductor is doing C, nothing. So this is question 5. It says a proton moving with V is equal to 10 to the 5 meters per second enters a room where E is equal to 10 to the 5 going to the right. If you do not want the proton's path to get deflected, what should the magnitude and direction of B, the magnetic field, be? So because it's a proton, a positive charge, it's going to be deflected to the right, which means we need a magnetic force that is pulling it to the left. If we write everything out, we have Fe is equal to Q times E, and then we have Fb is equal to QV cross V. We know that V, the velocity, is going in the positive y-hat direction, and we know that Fb has to be going in the negative x-hat direction, right? It has to be pulling it to the left. So then by our right hand rule, we can figure out the direction of B. What we're going to do is point our index finger in the direction of plus y. Our thumb is going to go in the direction of negative x. And then you see that your middle finger is pointing into the page. As for the magnitude, QE has to be equal to QV cross B for them to perfectly cancel out, which means that E is equal to VB sine theta, but because V and B are perpendicular to one another, sine of theta goes away. So that means that B is equal to E divided by V. If we look at the numbers here, E is 10 to the 5 newtons per coulomb. Divide that by 10 to the 5 meters per second, and that is going to give us 1 Tesla into the page, which is C. And that is it for that question. So we can move on. 6 says, what is the equivalent capacitance between points A and B? C equivalent, when they're in parallel, is equal to C1 plus C2 plus whatever. And then C equivalent, when they're in series, is equal to 1 divided by C1 plus 1 divided by C2 plus whatnot to the power of negative 1. We see that these are in parallel and these are in parallel. So then we get 10 microfarads, 10 microfarads, and 10 microfarads. Then we can just add them up because they're in series, and we get a final equivalent capacitance of 10 over 3 microfarads, or about 3.33 microfarads. And if we go here, that is D. 7 says, what is the current going through the 3 kilo ohm resistor, which is this one here? That is going to be I1. So instead of doing the whole like Kirchhoff's loop rules where we have one loop here, and a junction, well, we're just going to be looking at this loop, and that's going to give us everything we need to know. So this is our loop where we have 10 volts minus 3 kilo ohms times I1 plus 4 volts, because here we have another battery, minus I1 times 2 kilo ohms. And that has to be equal to 0. So that gives us 14 volts minus I1 times 3 plus 2 kilo ohms, so 5 kilo ohms is equal to 0, which gives us I1 equal to 14 volts divided by 5 kilo ohms, which is equal to 2.8 milliamps. And that is what we have right there. So here in 8, we have 2 long wires of length infinity, and they are parallel to one another. We are asked to figure out what the magnetic field is at this point here, when I1, the current in this one, is equal to I2, the current in this one. This was a long form question in the previous exam, so if you want, you can look at that, but we're going to quickly go over it here. The idea is to first identify where is the magnetic field pointing due to this current carrying wire. So you're going to stick your thumb out in the out of the page direction, and then you see how your hands wrap around in the counterclockwise direction, forming a circle like this. This is what the magnetic field looks like. So at this point here, it is going to be going tangent to that circle, which means it looks like this, and it has a 90-degree angle here. If we were to draw another triangle, this one is going to have 60 degrees, because this is 90, that means that this is 30. So then we can divide B1 up into its components. So B1x is equal to this here. And if this is the angle, well, that's going to be B1 cosine of theta. And then B1y is equal to B1 sine of theta, where theta here is just 30 degrees. And so we can do the same thing on the other side for B2, where now our thumb is pointing into the page, so our hand is wrapping around in the clockwise direction. And so at this point, our tangent line is pointing like that. So this is B2, same deal, this is 30 degrees. B1x is equal to this is B2x now. B2x is equal to B2 cos theta, and B2y is equal to B2 sine theta. Now hopefully you noticed that B1x is equal and opposite to B2x. So that means the net magnetic field in the x direction is equal to 0. And then in the y direction, they have the same magnitude. So this is equal to this. So then they add up. So it's going to be 2 times, say, b1 sine theta, where sine of 30 is just equal to 1/2. So then it's just this divided by that in the y-hat direction. So the net magnetic field is b1 pointing straight up. What is b1? Well, it's just the magnetic field of a current carrying wire, which is equal to mu naught I over 2 pi r, where r is the distance from your current carrying wire to the point that you're talking about. So if we look at our choices, here they're using L instead. It doesn't really matter. The answer is still going to be B, mu naught I over 2 times pi times L. In 9, you're told that you have a particle with a certain mass and a certain charge with a speed of 30 meters per second at point A, moving with only the electric force acting on it, to point B, where its speed is 80 meters per second. You want to know the potential difference between points A and B. So hopefully you remember that the link between potential energy, so say electric potential energy at point A, that's just going to be equal to Q times the electric potential at point A. So we can use our conservation of energy, where Ka, kinetic energy at point A, plus potential energy at point A, is equal to the kinetic energy at point B, plus the potential energy at point B, to solve for VA minus VB. So here we have 1/2 m UA squared, where U is just the velocity, plus Q times VA is equal to 1/2 m UB squared, plus Q VB. We want to solve for VA minus VB, so VA minus VB, and that's going to be equal to 1 over 2Q m UB squared minus UA squared. If we plug in all of our numbers, we're going to get 1 over 2, and then Q is 5 times 10 to the minus, 5 times 10 to the minus 9 coulombs, and then the mass of 2 times 10 to the minus 6 grams. And then the speed at point B, that was 80 meters per second. And that's going to be squared, minus the speed at point A, which was 30 meters per second, and we're going to square that. So if you plug in all of your numbers, you get delta V AB is equal to negative 1.1 kilovolts. So if you just plug in everything as it is here, you're going to get that negative sign. It's just saying that an increase in your speed correlates to a decrease in your potential. And so here we see that this is C. We're going to start our long answer questions now, where number 1 says, what is the work required to bring a charge plus Q from point D, which is this point here, to D over 2, which is this point here. So from A to B. The rod is uniformly charged. Essentially, we need to figure out what is the electric potential at this point and what is the electric potential at this point. dVA, the electric potential at point A due to a little bit of charge dQ, is going to be equal to Ke times dQ over R, where R is the distance from point A to our charge. We're going to define X as being the distance here to our charge, and then L is just the length of the rod. So that means this bit of charge is distance L minus X plus D away from point A. Now we're going to do the same thing for all of these little bits of charges all along the rod, where X varies from being equal to 0 to being equal to L. So we put that together and we get VA is equal to, and then we have Ke integral from X is equal to 0 to X is equal to L dQ, but remember dQ is equal to lambda dx here. So we're going to have lambda dx divided by r, where r is just the distance, and it's going to be d plus L minus x. Solve that integral, and we get negative Ke lambda ln of d plus L minus x, where x goes from 0 to L. Let's actually put in these bounds here. So we get negative Ke lambda ln of d plus L minus L minus ln d plus L minus 0. So that's going to be negative Ke lambda ln of d plus L. So d plus L minus L, so 0 is just d, minus ln of d plus L. We can do a few things here. The first one is combining like the natural logarithms, where we get negative Ke lambda ln of d divided by d plus L. We can also get rid of this negative sign by switching the numerator and denominator. So this is Ke lambda ln of d plus L divided by d. So that is VA, the electric potential at point A. We're going to do a very, very similar thing now for point B, where the only difference is R is equal to L minus X plus D over 2 now. So remember before it was L minus X plus D, now it's L minus X plus D over 2 because B is at this position right here. So if I write that out, we get VB is equal to Ke lambda, integral x goes from 0 to L, and then we get dx divided by d over 2 plus L minus x, and that is going to be negative Ke lambda ln of d over 2 plus L minus x, where x goes from 0 to L. Similarly, let's simplify this down. We get negative Ke lambda ln of d over 2 plus L minus L minus ln of d over 2 plus L minus 0. That gives us negative Ke lambda ln of d over 2 minus ln of d over 2 plus L. So similarly, we're going to combine these, and we get negative Ke lambda ln d over 2 divided by d over 2 plus L. Lastly, we're going to flip the numerator and denominator to get rid of that negative sign. So we have Ke, I should write it fully, VB, the electric potential at point B is Ke lambda ln of d over 2 plus L divided by d over 2. So if we remember, the question wanted to know what is the work done, or well, what is the work it takes to bring a charge plus Q from point D to d over 2. What this requires is the following, where work is equal to negative Q delta V, where delta V is equal to VB minus VA. And so this is going to be, well, we have VB right there, right? Ke lambda, and then we have ln of d over 2 plus L divided by d over 2 minus ln d plus L divided by d. So we're going to combine them as we have been doing, where we're just going to divide this by this. So essentially we're going to have this multiplied by the inverse of this, and that is going to be equal to Ke lambda ln, and then we have d over 2 plus L divided by d over 2, and then we have times d over d plus L. A couple things cancel. We have the d here and the d here. This we can then put in the numerator, right? So I'm just going to move some things over a little bit, where we now have Ke lambda ln of 2 times d over 2 plus L divided by d plus L. Okay, so this is the delta V, and then to figure out work, well, you're just going to say that work is equal to negative Q times delta V. So you take whatever charge you have, you're not given a value for it, but then your final answer is literally going to be this times negative Q, and then you're all done. In 2, we're asked to find the magnetic field at the center of two semicircular loops carrying current I. We're going to be using Biot-Savart's law for this, and we're going to start off by figuring out the contribution to the magnetic field due to these little straight lines of our current carrying wire. So ds is a little step along our current carrying wire. So here, this is the direction of ds, and here this is also the direction of ds. Now r hat is the unit vector going from our current carrying wire to the point of interest. So here it's going to be in this direction, right? Like this is r hat, and then here, this is r hat. We see that ds and r hat are parallel to one another. So they're parallel for both this part and this part. Because they're parallel, ds cross r hat is always going to be 0 for these two straight lines. Because this is 0, dB is equal to 0, so they do not contribute to the magnetic field at all. We're going to now look at the semicircles. So let's start off by looking at that smaller semicircle with radius a. So it looks like this. And again, a is just the radius. ds is a step in the direction of our current. So here the current's going in this direction, and it looks like that. So r hat goes from the current carrying wire to the point of interest like so. And see here they make a 90-degree angle. We want to know the direction of ds cross r hat. We're going to use our first right hand rule. So put your index finger in the direction of ds, middle finger in the direction of r hat, and you see your thumb is pointing straight up. So we're going to call this ds, and ds is always going to be in the plus k hat direction for this inner semicircle. And this one we're going to call 1. So 2 is going to be the contribution from the outer semicircle. This one has radius b, and here you see that the current is going in this direction. So this is ds, and then this now is r hat. Similar thing, point your index in the direction of ds, your middle finger in the direction of r hat, and you see how your thumb points down. So that means it's going to be ds in the negative k hat direction. All that's left to do is sum up the contributions of, well, like all the different parts of this semicircle and say, well, they're all going to the negative k hat direction. So let's go ahead and do that. We're going to call this B1 and say that B1 is equal to, then we're going to go down here, pull our B of sub r law, and B1 is equal to mu naught I over 4 pi a squared, because r is the radius here, we call it a, and then it's going to be the integral over the semicircle of ds in the plus k hat direction. So essentially we're just stepping along our semicircle and adding up their contributions. This integral is just going to be the length of this semicircle here, which is going to be pi times a. So probably didn't leave myself enough space. If you write it out, this is equal to mu naught I over 4 pi a squared, and then pi times a in the plus k hat direction. We see pi cancels out, and then an a cancels out, and we get mu naught I over 4a plus k hat. So for B2, the contribution due to the bigger semicircle, we get B2 is equal to mu naught I over 4 pi b squared, because it has a radius of b, integral over its semicircle of ds in the negative k hat direction, and that is going to be mu naught I over 4 pi b squared times pi times b in the negative k hat direction. So similarly, that's just going to be mu naught I over 4 times b in the negative k hat direction. So the total magnetic field, we're going to call B net, is equal to mu naught I over 4 times 1 over a minus 1 over b in the plus k hat direction. And that is your answer there. Problem 3 says we have a long wire carrying a current I1 is equal to 3 amps, shown here. We then have a rectangular loop carrying a current I2 is equal to 20 amps in this direction, shown here. A is equal to 1 centimeters, B is equal to 8 centimeters, and then L is 30 centimeters. What is the net force on the loop due to this current here? We know that the magnetic field created by that current carrying wire is equal to mu naught I over 2 pi r, where r is the distance from the wire to the point that we're talking about. We also know the direction of all the forces. So if we call this side 1, side 2, side 3, and side 4, and we use our, first right-hand rule, we can figure out the force because here, for instance, F1 is equal to I2L cross B1. So we know that the magnetic field is coming out of the page here and into the page here. We also know that here L, for instance, for this side, is pointing in the direction of the current through this wire. So here it's going to the right. I'll just draw that out for you guys. So this is L. Now by our right hand rule, you point your index finger in the direction of L, so to the right. You point your middle finger into the page, and then you point your thumb in the direction of F1. And we see that F1 is in this direction. You can do the same thing for F2, F3, and F4. So we don't have to worry about those directions. We just now need to know the magnitude of the force that they're experiencing. So let's go ahead and actually calculate that. Like I said, we have F1 is equal to I2, the current that's going through it, L cross B1. And that's going to be equal to, since they are perpendicular to one another, I should have emphasized that, where here we have L and then going into the page we have B1, so they're perpendicular, so sine of that is equal to 1, is going to be equal to I2 times the length times mu naught I1 over 2 times pi times A, because here A is the distance from our current carrying wire to the part of the rectangle that we're talking about, so distance A away. If I were to put in proper numbers, I'd have I2 being 20 amps, and then L is the length of that wire, which we know is 30 centimeters, so times 30 centimeters, times mu naught times I1, which is 3 amps, divided by 2 times pi times A, where A, we're told, is 1 centimeter. So times 1 centimeters, and that is F1. Okay, so that's the magnetic force F1 on this part of the current carrying wire. For F2 and F4, we know that they're going to be equal and opposite. The idea is they're experiencing the same magnetic field. One of them's being pulled this way, the other's being pulled that way, so they're going to cancel out. We can write that as F2 is equal to negative F4. Now F3 is going to be equal to I2L cross B1, where similarly it's going to be I2L, where L is just the length, and I guess I can put the actual values in. So I2 is 20 amps times 30 centimeters, because here we're talking about this one right there, and then it's going to be mu naught times 3 amps divided by 2 pi, and then the only thing that's different is this distance here. So here we have A plus B, so the distance away from these 2 points here. So A is 1 centimeters, and then B is 8 centimeters, so it's going to be 9 centimeters, so times 9 centimeters. And we know that F1 is pointing in the plus y hat direction, and then F3 is going in the negative y hat direction. So if we want to add up all these forces, we'd say that F net, the net force on this rectangle, is equal to, well, we have 20 amps times 30 centimeters times mu naught times 3 amps, right? So that's all the stuff that they share in common, divided by 2 times pi times 1 divided by 1 centimeter minus 1 divided by 9 centimeters, and that is going in the plus y hat direction. Okay, so I mean, obviously I didn't actually have to write it all out. I could have equally just said F net is equal to, we have mu naught L I2 I1 divided by 2 pi 1 over A minus 1 over A plus B in the y hat direction. But regardless, it's the same thing, and that is it for 3. In question 4, we have a square conducting loop of side A and resistance R passing through a region of space that has a uniform magnetic field B going into the page. We're going to assume that its velocity is constant, and we're going to calculate the magnitude and direction of the current in the loop. A as it enters, B as it's traveling inside, and then C as it exits. So we know that as it enters into this field, the flux, the magnetic flux inside this square is going to be increasing into the page. So that means that it's going to compensate by creating a magnetic field that is coming out of the page. So B induced is going to be in this direction. To get a magnetic field going in the out of the page direction in a square loop like this, I induced has to be in the counterclockwise direction. We know that because if you put your thumb in the counterclockwise direction, you get your fingers coming out of the page here and then going into the page here like we want. So what is the magnitude of I? Well, the magnitude of E is going to be equal to N d phi B over dt. There's only one loop, so we're just going to have N is equal to 1, so d phi B over dt. What is the change of flux over time? We know that d phi B is going to be equal to d of B dot A, where these are the magnetic fields and area vectors. We can define our area vector to be pointing in the same direction as B. So here we can say, well, they are in the same direction, they are parallel, so then the dot product can just go away. So then we're just left with d of B and then A. So what we can then say is that it is the area that is changing in time. What I mean by that is here, like as we are passing it through this region here, we are changing the amount of flux that is going through a little strip here, right? So it's like how much flux is going through this little rectangle is going to be changing with respect to time, because this here, this magnetic field is constant. Okay, so then we say that d phi B is equal to B times dA. So then when we go back here, the induced EMF is going to be equal to, we have B times dA over dt. Now what is dA? dA here, it's this little strip of area right there, which we're going to define as having length A, so that is A, times dx, which is a little strip of like width dx, and that is moving in time, right? So it's like a certain amount of this rectangle is passing into this region at any given moment in time. So we're going to write that out as B times A times dx over dt. dx over dt, that's just the velocity, so we can write it out as such. So that means the induced EMF is equal to B times A times V, and we know that that is equal to I induced times the resistance. Therefore, the induced current is equal to B times A times V divided by R for A. Now what about B? Well, B is when we have our square that is traveling within this region. We know that when it is fully in this region, and it's still in this region, there is no change in flux, right? Like we have magnetic field lines going in, and they're just going in and not changing. So because there is no change, it means I induced is equal to 0. As for C, well, we're asked, how does it change as it exits? Here, it's going to be essentially the opposite as it was when it was coming in. So same magnitude of current, but just in the opposite direction. So here we're getting a decrease in B going in the X direction. So then B induced is going to be going in the X direction. And to get that, we need to have the current going in the clockwise direction so that we have X on the inside and then dots on the outside. So I induced is equal to, well, I guess it's going in the clockwise direction with a magnitude of B times A times V over R. So just flipped directions, and that is all the question was trying to get you to do.